Okay, well, go ahead and get started. Today, our speaker is from the Department of Aeronautical and Astronautical Engineering. He is a grad student working on plasma thrusters, but he's working in the Earth and Space Science Department. So it gives you an indication of how cross-disciplinary some of the research on campus can be. He also has the distinction of being an alumni from this class because he was an undergraduate in UW and took this class while he was an undergrad. So with that, I will give you Ian Johnson.
Thank you. Good afternoon. Thank you all for being here. My name is Ian Johnson, as Erica said. I took this class back in 2006, and my current advisor, Dr. Robert Wingley, was speaking. He was talking about this M2P2 project, which was talking about beaming a small spacecraft between Earth and Mars. And that was when I decided I wanted to work in Robert's lab. So I emailed him a few days later, and he said, no, thank you, we have enough people. And that really kind of crushed my dreams. And then when I became a grad student, I emailed him again, and he said, oh, we'd love to have you. And I got my master's 2 years ago, and I'm now working on my PhD. So this particular seminar class was kind of the reason that I'm on the life path that I am at the moment. So I was very honored when Erica asked me to speak. I wanted to talk to you guys a little bit today about some of my work in electric propulsion, and in particular the difference between electric propulsion and chemical propulsion. Chemical propulsion is probably what we know more of. We think of the space shuttle, the Apollo missions, and the amateur rocketry that goes on. SpaceX has been in the news recently with their Falcon rockets and their Dragon capsule. Electric propulsion, on the other hand, is almost the complete opposite. Instead of a big flame that comes out the back, you have a very small amount of fuel. Space shuttle moves fairly slowly. Electric propulsion can move very quickly. Space shuttle uses up all of its fuel in the first 5-10 minutes of its flight, whereas electric propulsion can last for years or decades on end. And one of the current missions using electric propulsion is the satellite I have here. It's the Dawn satellite. It was launched back in 2007, and it's currently in the asteroid belt. It orbited around Vesta, which is the second largest asteroid in the asteroid belt. It's very dry. It's the largest asteroid, or it's the brightest asteroid that we can see here from Earth. It left Vesta last year and is currently on the way to Ceres, Ceres being the largest asteroid in the asteroid belt. And it's meant to dock there in 2015. If it's able to complete that mission, it'll become the first spacecraft to orbit 2 extraterrestrial bodies. Compared to, you look at the Apollo mission, which just went into orbit around the moon. The Voyager spacecraft, which were launched back in 1977. They're currently leaving the solar system. They just did flybys of Jupiter and Saturn. But the fact that we can go into orbit around 2 separate bodies is fairly impressive, and it's made possible through some of the work that I'm doing, although it was work done by people who are much smarter than I am, but work in electric propulsion and the efficiency of these EP systems. So you look at some of the fuel speeds, 31,000 meters per second, extremely fast, but the thrust is only 90 millinewtons. Think of a millinewton about being the force of you being hit in the head with a piece of paper. So just imagine you being hit with 90 pieces of paper every time this thing fires. That's all the force that this electric propulsion system is able to impart to the Dawn spacecraft. And yet, it's able to do that for such a long period of time where there's no friction or drag up in space that you're able to achieve these extremely high speeds. And with only 400 kilograms of propellant. And it's about halfway through that right now. So it has about 200 kilograms left. So today, there's kind of 3 points I want to hit on. The first 2 are much more important. Chemical propulsion versus electric propulsion will be the first half. And then some of the electric propulsion research here at the UW, my work in pulsed plasma thrusters and the high-powered Helican thruster. And I'll talk a little bit about some of the fusion research that we're doing over in the AA department. And then at the end, I'll talk about some of the people who have helped me, some of the people who are working in my lab, and then some of the other opportunities that are available to you guys as undergraduates at the UW, and opportunities that I really wish I'd taken advantage of in my 4 years as a student here. So chemical propulsion. A chemical reaction is simply taking 2 reactants, mixing them together. You get a very hot substance moving at a fairly high rate of speed, and you expand that out of a nozzle, and that creates thrust. So that's the big flame that you see out the back. There's three fairly common types. The one we're most familiar with is solid propulsion. So on the space shuttle, you have the small white tanks on either side. Those are the solid rocket boosters. The large orange tank in the middle is the liquid fuel tank. Amateur rocketry is almost all solid fuel because it's easier to use. There's a class that I TA'd last year, ESS 472. They go down to the Black Rock Desert, where if you've ever heard of the Burning Man Festival, they hold it in the same place because it's in the middle of nowhere and no one can see them drinking and smoking. We go there because we can crash rockets into the ground and there's no towns around for us to hurt anyone. But all the rockets you see in that picture are solid rocket boosters. As I said, the large orange tank on the space shuttle is a liquid booster, and then SpaceX, which has got in the news last year in particular, sending the Dragon capsule up to the ISS. That's all liquid propulsion. And then Richard Branson, he just had his first supersonic flight of Spaceship Two. That's a hybrid rocket motor, and hybrid is simply exactly what it sounds, a mixture between solid and liquid. So the space shuttle obviously has been around forever. The Apollo missions back in the 60s, those were all solid fuel. All the work that the Russians are currently doing, getting to the space station, that was all solid fuel. That is all solid fuel. There are millions, tens of millions of hours of flight time with chemical propulsion, and that's the largest advantage that chemical propulsion has. We know how it works. It's about as efficient as we can possibly make it. It's just a reliable propulsion source, which is why that so many satellites use it today. The performance, you get high thrust in the meganewton range. If a millinewton with electric propulsion is the force of a piece of paper hitting you, a newton is going to be the force of an apple hitting you in the head. So imagine a million apples hitting you in the head for, in case of the space shuttle, a 10-minute flight, and that's how you get up into orbit. Very short duration, 5 minutes, 10 minutes, maybe an hour if you're lucky, and a fairly low fuel speed, only about 11,000 miles per hour. So when I was younger, there was a character that I was extremely fond of, I suppose, and I relate him to chemical propulsion. Paul Bunyan, really big, moves pretty slowly, methodical, not a whole lot of speed, not very efficient. And when I first started learning about chemical propulsion, I was associated with Paul Bunyan, and I think that's an easy way to remember what it is. Interesting side note that I didn't know until I was researching this talk. I always assumed he came from the 1700s, back when we founded this country. Turns out he was invented in 1906 by a Michigan author who was looking to save the environment, and he came up with this character who cuts down a whole lot of trees. So when he first was around, he was actually a bad guy, and Michigan was trying to portray him as someone who we don't want to follow, and today that's been completely twisted around as someone who has founded this country. Anyways, that's not important. Moving on. So some of the chemical propulsion here at the UW, these are two classes that I've both taken a part of, either TA'd or been involved in. So there's a special topics class in the aerospace department. They create one pretty large rocket. You can see it here. They have one competition a year. Usually they come in first or second place. The point of this competition is launch a rocket typically up to 25,000 feet, so about 5 miles up. You want the parachutes to deploy. You want apogee to be right at 25,000 feet. The closest rocket that gets to 25,000 feet and survives on the way down ends up winning. And as I said, they usually come in first or second place. I have a number of friends who were involved in that last year and a couple of friends who are, again, involved in that this year. But a class that is available to each one of you if you want to get involved in it. And then ESS 472, which I've been involved in for a little longer. This, instead of entering a competition with a whole lot of other people, we just build rockets for fun. So we have about 50 launches a year. This is me down in the Black Rock Desert before my level 2 cert flight. And then we do a lot of, instead of just launching a rocket off from the ground, which gets boring after you've done it for a few years, we do some other things. So this was a Raccoon. We put 2 balloons up in the air. This was up to about 2,000 feet. And then we launch a rocket from there. The thought being that if you can send the balloons up to, I don't know, 100,000 feet or so, you get an extra 100,000 feet of altitude on your rocket flight. So we did a tethered launch up to about 2,000 feet this year, and we're hoping next year to write a proposal to go out on the UW research vessel, the Tommy Thompson, into the middle of the Pacific Ocean, where we can send this balloon up and launch a rocket. And the reason we have to go in the middle of the Pacific Ocean, there's no region large enough in the US where nobody lives. So it's going to go up to 100,000 feet, but it could drift for 20 miles or 50 miles on its way up there. And when we actually fire it, we have no idea if it's going to be over a town or whatnot. So we need to go out in the middle of the ocean where we're only going to destroy, I don't know, some fish or something that's out there. And then the other one that we do are these night launches. These is probably my favorite part of the trip, although also the most dangerous. So you get these fantastic pictures. On the other hand, once the burn stops, it's pitch black outside and you have no idea where it is. So you're all hiding, hoping it doesn't come back down on your head or that the parachute actually deployed. So it's an incredible amount of fun. But also we're all just kind of huddling there thinking, is it going to hit us? We have absolutely no idea. So most of those 50 launches in ESS 472 go well. Every once in a while, one doesn't. This is a camera that we put on the outside of a rocket from last year, I guess. And the parachute doesn't fully deploy on this. So hopefully the sound still works. But this is one of the rockets where it goes up, it comes back down, and you just hope it's not coming back down at your head. And so you can see we put a lot of time, effort into this, and it impacts the ground and completely destroyed. We weren't able to fly this rocket again. But you can see it was up looking at the clouds, blue sky, and then it pitches over. And that's right when everyone starts, well, swearing and running a lot. So good times. And there's another class at the UW that a little less powerful chemical propulsion, one that Erica actually teaches, ESS 102. We have a fire extinguisher on a little red wagon, and same concept. You shoot the chemical reaction out the back, you go forward. You might have seen the class out down by Drumheller Fountain. They were launching off some small rockets, bottle rockets. They fill it about a third of the way with water, pressurize it up with a bicycle pump, and then launch them off. So a lot of opportunities at the UW to get involved in this type of research. So let's go into a little bit of science. You take any rocket, whether one that we launch off, one of the bottle rockets that ESS 102 launches, or something that NASA does. So you have three different sections. You have the payload. That's the important part. That's the humans. That's the science. That's life support, communications. That's all the stuff that you need to survive. That's what you want to take to the moon or to Mars or the asteroid belt, wherever. Then you have the structure. That's what's there to house everything together and keep the payload alive. So the rocket, various vacuum pumps, gas tanks, structural support, nuts and bolts type of stuff. And then you have the fuel. The fuel is what you expel out the back. So when you launch from the Earth, you have all three of these. After the burn, your fuel's gone, so you only have the payload and the structure, so it's a lighter rocket. Conservation of momentum, mass times velocity. The velocity of the spacecraft times the mass of the spacecraft needs to equal the mass of the fuel times the velocity of the fuel. Fairly straightforward. Except that the fuel isn't launched, isn't expelled at the same time. So you would think that to go faster, you need to maximize the fuel speed, maximize the fuel mass, and minimize the mass of the craft. Thrust isn't instantaneous. So because the thrust doesn't occur at exactly the same time, take the space shuttle, the burn's over 10 minutes, we have to modify that equation. So instead of just mv in equals mv out, all we have to do is add this natural log term. It's not overly confusing. The velocity of the craft equals the velocity of the fuel times the natural log of the mass fraction. So you have the fuel plus the craft, which is your initial mass, and then just the mass of the craft after the fuel is gone, or the final mass. So it's the natural log of the initial mass over the final mass plus a constant. So we can take this equation, and we can say, all right, if we're in orbit around Earth, and we want to go to Mars and return, we know that they're a certain distance apart. We need a certain speed to get there. Using mathematical formulas and whatnot, we can calculate that the speed required to get to Earth or to get from Earth to Mars and back is 14,000 meters per second. So we can plug that number into our equation here. With chemical propulsion, fuel speed of 5,000 meters per second, we can get that we need 15.4 times more fuel than whatever the payload and structure is that you're trying to take there and back. So 15.4 isn't that bad. I weigh about 150 pounds, so if I wanted to send myself to Mars and back, I would need about 2,300 pounds of fuel. Not unreasonable. I just need to go to the gym a bit more, as I can't currently lift 2,300 pounds of fuel. But then let's say, all right, Mars is boring. We want to go to Saturn and come back. Saturn is a little further away. It's a little heavier, so it'll take more speed or more fuel to get into orbit and more effort to get back out of orbit. So instead of 15.4, we need 3.6 billion. If I can't lift 2,000 pounds of fuel, I'm certainly not going to be able to lift billions of pounds of fuel. So this is a problem. There's not a whole lot we can do to change this. If we take our spacecraft of me, 150 pounds, I could go on a diet so we could reduce the mass of the craft, but I can't lose that much weight. So what we really need to play with is the velocity of the fuel. So instead of chemical propulsion at 5,000 meters per second, maybe we go to electric propulsion, or my research, at 25,000 meters per second. So if we plug this 25 kilometer per second number into our equation, we get that to get to Mars and back from Earth, we only need 1.8 times as much fuel. To get to Saturn and back, we need 81.5, which isn't unreasonable. It's a large number, but it's drastically less than 3.6 billion. And when you look at, so that's just the mass to get there and back. You also have to put the mass up into orbit. SpaceX has a new rocket coming out. They're hoping for 2014 called the Falcon Heavy. It's a chemical propulsion system. It's liquid propellant. The cost to get to orbit is about $4,000 per kilogram. So you can imagine if we want to send me to Mars at 2,300 kilograms of fuel at $4,000 per kilogram, that's quite expensive. And especially if we're trying to go to Saturn and we can reduce the amount of fuel we need from 3.6 billion to only 81.5, that's a drastic improvement in the savings. And I should mention the cost to orbit, $4,000. That the space shuttle was $10,000. So this price is coming down, but with chemical propulsion, it's really not going to get much below 4,000, maybe 3,000 if some engineers can really get their heads together. So talking about electric propulsion, the question always is, what is it? What's special about electric propulsion? It involves plasma. When I talk about plasma, people get fairly excited. They think it's some fancy science term. It's really not all that complicated. We all know if you take a solid and you heat it up, you get a liquid. If you take a liquid and you heat it up, you get a gas. What happens if you take a gas and you heat it up? You simply strip off the electrons from the ions, and you get this electrically charged gas that we call a plasma. It's the fourth state of matter. It makes up over 99% of the universe around us. And these are just a couple of the pictures. A little plasma ball that costs about $5 on eBay. Lightning, the aurora, if you've ever been up into Alaska or Canada, some lucky days when it's very dark outside, you can sometimes see it from Washington. The sun is almost entirely plasma. Any flame, fireplace, whatever. And then you get some more interesting experiments. This is at the Livermore down in California, where they shine a bunch of lasers at a small pellet, heat it up, and that's how we get fusion. And then the high-powered Helican, the thruster that I work on, is shown there as well. So Hollywood has a lot of fun with plasma and fusion science. One of probably the worst movie that I've seen recently, Spider-Man 2, Dr. Octavius, he created this giant glowing ball and said, this is fusion. It's magnetic fusion. It attracted everything towards it. Spider-Man almost died. It was very terrifying. The science was actually pretty good. Magnetic fusion is a real thing. We work on it here at the UW. I have a number of friends who work in the labs and know quite a bit about it. But this is why plasma science and plasma physics gets a bad rap, because Hollywood takes these concepts and then just blows them up to extreme features where you get people with crazy arms trying to work on it. Where it's not that far off in the future. We're getting extremely close now. So electric propulsion, complete opposite of chemical propulsion. You have very little flight heritage. Chemical propulsion had tens of millions of hours of flight heritage. Electric propulsion, even though it's been around for the same time, really only has, I don't know, a few 100,000, if that, hours of flight time. One of the first satellites that went up with an electric propulsion thruster was by the Russians. It was called Zond 2. It was supposed to go to Mars. It involved pulse plasma thrusters, which is the same thing that I worked on. The pulse plasma thrusters worked great. The communications on it worked less than great, and they lost contact with it about halfway there, so it's still floating out in the solar system somewhere. One of the more recent electric propulsion satellites was the Earth Observing 1 satellite. It's in low Earth orbit around the Earth, and it uses pulse plasma thrusters to position its cameras very, very precisely so it can take pictures of the Earth for environmental reasons. So extremely low thrust. As I said, the maximum thrust is in the millinewton range. Again, force of a piece of paper hitting you in the head. You have a fairly long duration. The space shuttle uses up all that fuel in about 10 minutes. EO1 was launched in 2001, and it's been going on for 12 years now. Very high fuel speeds. Instead of 2 to 5 kilometers per second, you get 25 kilometers per second. And in our lab, when we use a very light propellant, such as hydrogen or helium, we can get speeds of 90 or 100 km per second. Yeah, nothing special there. So Paul Bunyan was my example for chemical propulsion. Another one of my childhood favorites, the Roadrunner, is my example for EP. Very fast, clearly not a whole lot of muscles, doesn't go to the gym every day, but very efficient, can move much quicker than Paul Bunyan can. So transitioning now to some of my research. This is a complicated slide, I apologize. But so we work on the high-powered Helican. You can see it firing here. So the Helican antenna, that's the special part about this particular thruster. You can see it down here. It's this, you just take 4 wires and you twist them into a helix similar to DNA, and we run current through it. So about 1.5 kiloamps or 20 kilovolts, and we can run it for 200 microseconds, 500 microseconds, up to a millisecond. So we get power levels on the order of a megawatt, somewhere in there. So that Helican antenna, that's the special part about this device. That's what ionizes the propellant. Typically, we pump in argon gas. That antenna also creates a wave. That wave attaches itself to the base magnetic field. Nothing overly special about a magnetic field. If you've taken a physics class, you run current through a loop, right-hand rule. Your hand twists in the direction of the current. The thumb points in the direction of the magnetic field. So you can see 6 of our magnets down here. The Helican antenna sits inside of it. We create all this plasma. We create this Helican wave that attaches to the base magnetic field moving into the chamber. The propellant attaches itself to the wave, and we get thrust. The impressive part about the Helican thruster is that we're able to get a plasma fraction greater than 90%, and some argue greater than 95%. So what that means is if we pump in 1 gram of fuel, 90% of that 1 gram will become plasma. And that's extremely hard to do. You take the pulse plasma thruster, which I'll talk about in a second, that only gets maybe 10%, maybe 15%. 90% plasma fraction is incredibly high. The downside of this device is all that fuel that we have to pump in. You need gas tanks, you need tubing, you need valves. All of this is under extremely high pressure. It costs a lot of money, and it's fairly complex. And being the guy who has to fix things in the lab when they break, complex is not something that I'm really going for. So if we could find a way to reduce the mass, the volume, the cost, and the complexity to this device, I would be extremely grateful. It would make my life a whole lot easier, and I think it would create a better thruster on end. And so in that regard, instead of pumping in the argon gas in the back, if we can replace that with another device, such as a pulse plasma thruster. So what we want to do is take a PPT, spew all these particles into the helican, and then have the helican ionize it further. So the pulse plasma thruster, compared to the helican, which is a fairly complex device, the PPT is fairly straightforward. You can see it's about the size of a quarter. You have an anode and a cathode, simply 2 electrodes. They're about ½ inch apart here. You're going to put a large voltage or a large electric potential across these two with a capacitor bank. You have a spark plug that's going to go. It's spark plug just like you'd have in your car, nothing overly special about it. When the spark plug goes, it completes the circuit and allows current to flow between the anode and the cathode. When the device fires, you get this nice white, blue, somewhat purple plume that comes out. It's really incredibly simple. You have a capacitor, you have a spark plug, you have 2 electrodes. This fuel in the middle is Teflon. Teflon is what you might use to cook at home, or we're in college, so what your parents might use to cook at home. I certainly don't. Don't tell my mom. But Teflon is simply made up of carbon and fluorine, C2F4. So when we create plasma, we get carbon plasma particles, fluorine ions, CF2 particles, a whole host of various ions. This is the device here in the chamber. And a few months ago, one of the undergrads in our lab wanted to do an experiment just to show how much force we actually get from the PPT. So we have the pulse plasma thruster here. We have a piece of tin foil. Tin foil is extremely light, sitting in front of it. And we're going to fire. I'll replay this video twice. What I love about this video is we have all this very expensive, fancy equipment in our lab. And our undergrads, and myself included, just because it's a good time, we don't always use all the fancy equipment. So you can hear some of the background chatter. It's what we are qualitatively assuming to be the performance of this thruster. So I'll play it twice. Pretty far out. $100,000 worth of equipment, and all we can get is pretty far out. I'll play it one more time. So again, this is just about the force of a couple pieces of paper hitting this tin foil. I love that clip. Anyways, so the current pulse we get from this, before the spark plug goes, obviously no current is flowing. When the spark plug discharges, we get about 5,000 amps of current. It lasts for around 100 microseconds. That's fairly impressive, but nothing overly special. So PPT works by ablating off the solid Teflon, which is made up of carbon and fluorine. You get a plasma fraction of less than 10%. As I said before, it's not all that great. But then we can accelerate these particles, typically at 20 to 30,000 meters per second. But we've recorded speeds up to 50,000 meters per second before. And since it's so simple in its operation, you're able to have it last for an extreme amount of time. The EO1 satellite, which I showed a picture of before, launched in 2001. The whole thruster weighed 5,000 grams. And over the last 12 years, we've been able to get 12 million pulses out of it, so about 1 million pulses a year. So apart from just assuming, wow, that went pretty far, that was cool, we actually do some real science in the lab. This probe that sticks up right here is the double Langmuir probe, named after Dr. Langmuir from early 1900s. He was somewhere back on the East Coast. This probe simply has 2 tips that extend into the plasma. As plasma flows between those 2 tips, you get current that's allowed to flow. The more current that flows, the more voltage that gets out. You're able to get more current flowing if you have more plasma. So it's a way to measure the density, in particular the electron density of the plasma that's moving through it. Since you create the same number of electrons as you do ions, we assume that whatever the electron density is, that's going to be equal to the ion density. And so the total plasma density is going to be twice whatever we measure with this probe. So this is simply zoomed in on the probe, but you can see the 2 tips coming out here and a quarter behind it. So it's really pretty small. So my whole research is about taking this high-powered helican, replacing the argon gas feed with this pulse plasma thruster. So this will be, I promise, one of the last technical graphs I show. But this is simply a graph of the density, or the output from this Langmuir probe. So with our solid fuel, PPT-based high-powered helican, we get this red trace. So you get density that comes up to around 7.5 times 10 to the 17 particles per meter cubed. All that means is if you take a meter cube, you get 7.5 times 10 to the 17 plasma particles inside of it. Nothing overly special about that. It's just number divided by a volume. And it extends out for about 200 microseconds, which we like that this peak is so high. We don't like that it doesn't extend so far. So you compare the solid fuel graph to what our typical trace is when we pump argon gas into the Helicon, and that's this blue graph here. You get about 5 times 10 to the 17 particles per meter cubed. So a slightly lower peak density, but you can see this extends out for about 400 microseconds. So about 3 times as long as with the solid fuel. So the solid fuel, 70% higher peak density, and you can see that this peak arrives slightly earlier than the vast majority of this blue curve, so we can say we get a velocity that's 9% higher. Although if you take the area under the curve, do a little bit of calculus, the total density of the argon is 156% higher than with the solid fuel, and that means that we end up with a higher thrust with the argon gas. So to improve matters, to increase the thrust, we need to increase the fuel produced. We need to take this red curve and extend it out. So instead of dropping down here, it drops down out here. So we want a larger area underneath this red curve. Up in the Advanced Propulsion Lab, we're looking at 2 ways to do this. So I've just overlaid the 2 current traces. You can see that the Helicon current trace goes on for much longer than the PPT current trace. So we need to, the first way is we need to extend, we need to make larger this blue current trace from the pulse plasma thruster. This is, I guess, initially a fairly complicated looking equation, but it's simply a decaying exponent multiplied by a sine term. So to extend this pulse out, we need to play with the natural frequency, which is here 1 over the square root of the inductance times the capacitance. And that'll extend the period out, so it should oscillate for longer. And then to increase the peak of it up here, we simply take this first term, the voltage, and the capacitance are on top. So to get a higher peak, we need more voltage, we need more capacitance, and then we need to lower the inductance. So we can go from 5,000 amps up to 10,000 amps, and we can go from about 100 microseconds out to 500 microseconds. And in the world of pulse plasma thrusters, that's actually fairly impressive, and we were extremely happy when we got those numbers out. The second way, which I suppose is a bit more interesting, and certainly more interesting to Earth and Space Science students, we can use different fuels. So typically we use Teflon. It's made up of carbon and fluorine. Teflon doesn't react with anything. It's safe. We use it at home to cook with. Then we've tried sulfur, which you can see here. It's the yellow thruster up here. If Teflon is safe, sulfur is the exact opposite. There's the smell. It reacts with copper. It does very, very bad things to the vacuum chamber that I end up spending a very, very long time cleaning up. But it has a higher vapor pressure, meaning it's easier to get particles off. As you pump down on the pressure, more stuff is just going to come off. The energy required to ionize the sulfur particle, so to go from a gas to a plasma, is lower with sulfur than it is with Teflon. So the first point, we should be able to get more particles. The second point, once we have those particles, we should be able to get more plasma out of it. And then it also has a higher mass. If you imagine if you play baseball or softball, if you get hit with a baseball, it's moving at a pretty high speed, but it hurts, but it doesn't hurt that much. Talk to a softball player, it's moving slightly slower, but because the ball is so much more massive, it leaves a much larger bruise on you. So sulfur, slightly heavier than carbon and fluorine, it's going to impart a little bit more thrust. And then we've also been looking at some metals. The metals have been a bit interesting, especially because, as far as we know, no one else has ever done this. So bismuth sulfide, B2S3, chalcopyrite, which is just a type of pyrite. It's a fairly common mineral you find around the Earth and up in space. And then also this magnesium-iron mixture. So we can see a couple of these particles here. We got bismuth, we have pyrite, we have magnesium iron, and then just a epoxy one that we made for fun because we, I don't know, have too much time on our hands, I suppose. So the pyrite has already been fired. The bismuth has already been fired. We haven't fired either of these two yet. And so that's going to happen in hopefully the next couple weeks. So I've been talking a lot about thrust. How do we actually measure thrust? In our large vacuum chamber, I'll show a picture of it in a bit, We have this very fancy thrust stand. It uses a laser to measure how far the pendulum moves. We get very precise results. People in scientific fields are fairly impressed. For our bell jar, just comparing these results, since it's more of a kind of a freshman, sophomore, junior, senior project, we don't use such fancy results. We took a pendulum that took about 2 hours to make one afternoon. So we have this pendulum here in front of the thruster. If you remember high school physics classes, if the pendulum swings out so far, how much force has been imparted to it. Same type of concepts, things like moment of inertia, angular momentum, all those concepts apply. So I'll play this video here for a second, and I'll replay it again a second time as well. You're going to see the pendulum swing out using a camera that we bought at Radio Shack for about 20 bucks. We can see how far it goes. We can freeze frame it. Knowing how much it weighs, knowing the moment of inertia, we're able to calculate the thrust imparted. So you'll see a bright blue flash right in this discharge region, and then you'll see the pendulum swing out. So 4 degrees, that's a fair amount. Imagine you're just hitting it with a piece of paper. That's actually fairly reasonable. So we put 1.4 kilovolts, 66 joules, fairly high powerful shot, but nothing overly special. From videos like this, we can take a number of these using different thrusters at different voltage, capacitance levels, and we're able to get graphs that look like this. So our Teflon thruster up here in blue, we got thrust on the y-axis, energy on the x-axis. You get about 10 millinewtons per kilowatt. So for every kilowatt that you put in, we get 10 millinewtons of force out. And that, as we increase the energy, that stays fairly constant. Then we go to our metal fuels, bismuth sulfide, and we get that number about doubles up to around 20 millinewtons per kilowatt. But then sulfur, as I was talking about earlier, that's kind of the special one. That's what we've been very proud about so far. We can get numbers up here of 45, almost 50 millinewtons per kilowatt, which is about 5 times as high as Teflon. The EO1 pulse plasma thruster, the commercial product, what the pros made, it's based out of Teflon. So their Teflon thruster beats our Teflon thruster, but their Teflon thruster is only on par with our metal thruster, and our sulfur thruster clearly outperforms it, which we've been extremely excited about. So just as kind of a summary of the thrusters that we are working on here at the lab. So we have our Teflon and our sulfur pulse plasma thrusters. Sulfur has higher thrust, but Teflon, because it's lighter, you get higher speeds. It's easier to get a baseball going faster than a softball type of thing. And then we have our gas-fed high-powered helicans. So with hydrogen, we get an extremely high rate of speed because the mass is so low. But with argon, a little heavier, we get an extremely high thrust. And then my PhD work is combining these two. And at the moment, we get a slight increase in speed from the PPT and from the argon thruster. We get a drastic increase in thrust compared to the PPT. But because we're not able to impart all that many particles into it yet, the thrust of our solid fuel device is still less than the thrust from the gas-fed device. So that's something that we've been working on. And then, so that's kind of the end of my science portion of this. In my last 5-10 minutes, I wanted to talk a little bit about the people who I work with and the opportunities that I've taken over the last 4 or 5 years. Because I simply don't do this myself. I didn't teach myself. I had a number of mentors. One of them being Dr. Robert Wingley, who's the chair of the Earth and Space Science Department and the head of our lab. This is a few pictures of him. This one, I just Google searched his name and I found it online. And when I looked at it, I said, "Oh, Robert, was this taken when you were in grad school? You look pretty young in this." And he goes, "No, that was from 10 years ago." So I upset him a little bit there. I think he's going to cut my funding. He's the instructor for the rocket class 472 that I was talking about earlier. This is one of the thrusters that he's created. To my knowledge, it's the largest rocket that we've launched from the Earth and Space Science Department yet. He's slightly shorter than I am, about 5'5". So this is, I don't know what this is, 9 feet, 10 feet tall. This is one of the thrusters that we have in our lab. It would bolt onto one of these large flanges here on the door of our chamber or over on the side. And as I said, this was M2P2, one of the projects that started our lab about 10 to 13 years ago. So we got our large chamber. It's 5,000 liters. It takes a few days to pump back down to space-like conditions. We have our smaller bell jar, which is where all those thrust stand shots, videos that I showed you came from. This guy is 5,000 liters. The bell jar is about 50 liters, so about 100 times smaller. And then you can see some of our control computers over here in front. So in our lab, Robert is our boss. Then we have Race, myself, and Now. Race has been in the lab for a few years. He's writing up his PhD thesis at the moment. I'm about halfway through my PhD work. I'm really hoping to graduate 2014, but we'll see how long Robert keeps me there. And then Now just started in our lab. We have a whole host of freshmen through seniors who work with us. A number of them, all of them are students at the UW. A number of them are Earth and Space Science majors. And just a few pictures of them. One of the cool projects they did, in addition to just the science that we do a number of outreach events. So Craig, Eleni, and Brenna went to Washington Middle School, which is just down the road, and spent a whole day talking to kindergartners through 6th graders, and I guess in middle school, so up to 9th grade as well, about some of the work we do in plasma science and the science research that we do here at the lab. They had a blast. And just to make fun of Craig, these were the only 2 pictures I had of him, and he's wearing the exact same clothes. They were taken about 2 months apart. He's not going to like it that I showed both of these. It said we go down to the Black Rock Desert. Sometimes the rockets don't go exactly where we want them to, and they impact the ground when the parachutes don't come out. So this is Chad Truitt and Robert digging a hole in the ground to get one of the rockets back out. Race here sitting inside of our vacuum chamber, and then 2 other pictures, one of our thrust stand with an old grad student we had, and Reese working on the other side of our chamber. So in addition to just us at the lab, we partner with a company, Eagle Harbor Technologies. They get a number of grants from the UW, from NASA, DOE, the Navy, all sorts of people to work on various things. It was started by Dr. Tim Zimba, who got his PhD from the UW, I believe in 2004, 2005, somewhere in there. It's about a 10 to 12 person company, and they are extremely good. They're based just down in Lower Queen Anne. They're extremely good about hiring students and giving opportunities to students, especially people from the UW through the Space Grant Office, which is one of the groups that sponsors this class. They currently have 4 students. Alex in particular, is my laser working? He's having a good time doing, I don't know, whatever it is that he's doing. He was just hired. He was an intern about 2 months ago, and he was just hired full-time by this company. But they do a lot of fairly interesting work. I interned for them a few summers ago. This was my project, a little electric thruster. This whole thing's only about 3 inches long, extremely small. It's supposed to fit in a CubeSat, if you've heard that term before. Some of the work that they do, fiber optic equipment, so we don't have to run voltage back to our control system, possibly blowing up computers. We can transmit and receive signals just with bursts of light. This is one of their first generation power supplies, and then one of their newer power supplies that they just put on the market, I think about a month ago. They've only sold 3 or 4 of them so far. These guys range about $1,000 a pop. Julian, who was in the last slide, last summer, they hired him to work on this railgun concept. So you switch this current back and forth very quickly. You build up force on a metal disc. It was about, I don't know, about the size that I am. And then you shoot that metal disc up in the air about 20 feet. Made an enormous sound when it hits back, comes back to the ground. They flew him down to Texas to go show that off at a conference they were having. And then they also have a host of plasma sources. This was a small little one that they started with, and then this is their larger one, which looks somewhat similar to what we have at the UW. So they're doing a lot of very interesting research. A whole host of companies in Seattle. We live in a fairly impressive part of the country for students getting involved with these groups. You don't get paid an exorbitant amount of money, but it's more than you would working at a library or a McDonald's, Safeway, something like that. So also here at the U, I was talking about Dr. Octavius earlier and some of the work that he's doing in Spider-Man. These 3 labs in my department, AA, we are actually doing what he did. So the HIT-SI lab is shown over here. A Spiramac is simply a torus-shaped fusion device. A torus is just a fancy word for something that looks like a donut. You can see half of it right here. They create a plasma. If I was talking about stuff that we do, 1.5 kiloamps, stuff like that. They'll get up into hundreds of kiloamps ranges up there. A whole lot of power. They're probably the closest lab that UW has to creating fusion, and they're also the largest fusion lab we have on campus. The ZAP lab, it's a Z-pinch, so instead of a torus, you're just going to have a long axial tube, and you can see that here. They are also working on fusion propulsion. And then the plasma PDL is over in Redmond. It was started by Dr. John Slough, who's got his PhD here from the UW as well. They were in the news last month. The UW kind of really publicized it. Some of you might have heard about it. He's claiming that with his fusion technology in 5 years, he can send a satellite to Mars and back in 30 days, which we all laughed at when we heard. We'll see if it comes true. But this was a little SolidWorks drawing that they made up. So a lot of work being done here. All 3 of these labs take student interns. A lot of opportunities to get involved in this type of work. So in conclusion, my last slide, what I really wanted to highlight, chemical propulsion, you need that high thrust to get out of the atmosphere. But then because it's such a low speed in a short amount of time, it's not so good for getting anywhere past the moon or Mars. You take electric propulsion, low thrust, so it can't get out of the atmosphere, but the high speed and the high burn time allows you to go much, much further. And then here at the UW, I'm working on the high-powered Helican, pulse plasma thrusters, but there's a whole host of other opportunities for you guys to get involved in this work. So thank you very much. Erica, thank you for having me speak here today, and I'd be happy to take any questions.
And they claim that they are ready to send a mission to Mars now. One of the online viewers wanted to know what your thoughts are on that claim.
So I like VASMIR. You take a high-powered Helican, you create all this plasma, and then you accelerate the particles further with this radio heating that they have. The company is called Ad Astra. They're based down in Texas. It's run by an ex-astronaut of NASA, so he has a bit of an in there. They're actually putting up a VASMIR thruster on the International Space Station. It was supposed to go up last year, but like with anything with NASA, it's over budget and behind schedule. So maybe this year, probably next year, if it goes up at all. But I like what they're doing. They have a lot of funding, a lot of political support. So I think they certainly have one of the best options or the best paths going forward to put something up in space.
Any other questions?
Yeah. Yep.
Once you reach the destination.
Yep. So with chemical propulsion, you get a really high burst of speed, and then you just float along forever. And then when you get to the planet, you turn the spacecraft around, and another high thrust burn to slow it down. Electric propulsion is the exact opposite. You're going to spend half your journey speeding up, and then turn it around, and the other half of the journey slowing it back down. So yeah, it takes a long time to speed up, and it takes a long time to slow down. But the speed that you're able to get there in the middle, so much higher than what you can get with chemical propulsion that you're actually able to get there sooner. But yeah, absolutely, it's a problem.
My question, how do the metallic fuel types work, like olivine, chalcopyrite, how exactly is that fuel source?
So everything here is created of electrons and ions. I could take one of these chairs, put 2 electrodes, an electrode on each side of it, run a current pulse, I would create plasma and shoot it off. I could do that with my computer, I could do that with whatever. It's just that some particles have higher vapor pressure, lower energy required to ionize, so it doesn't really matter what we use, it's just going to turn out that some are better than others. The problem with the metal fuels is that they weigh so much more, so it's just like, take the baseball, softball analogy. it's easier to hit a baseball further. It's going to take a whole lot more energy to hit a softball as far, but when it's traveling, it'll impart a whole lot more force to something that it hits. So I think we're going to take one of these heavier metallic fuels, and if we can hit it with a high enough energy, we're actually be able to get more thrust out of it in the end. But yeah, it's a good question. It's a very good question, something that we're looking at as well.
Thank you.
Thank you.